All right, y'all. So, don't really plan on doing any fancy intros or anything to this video. This one's going to be a bit less formal. So, I wanted to just take this week's asynchronous lesson and actually use it to just discuss some of the ideas from our slides, from the week 7, day 1 slides that we did on Tuesday. So, to start things off, let's go ahead and look at. I'm going to start at slide 5. I think that people could, are probably fine before that. In fact, I think people were probably fine up until slide 9, but I just want to quickly go over 5 through 8. So, first of all, one idea real quick. I want to talk about kind of what I was talking about here, like the difference between exponentials and logarithmic and how they're similar. So, in general, y'all, an exponential equation would be something of the form like, you know, 3 to the power of x equals, in fact, actually, you know what, let's not even use numbers. Let's use all variables. B to the power of x is equal to y. That's an exponential expression. Now, what you'll notice here is that b is the base. B is the base of this exponential, all right? B is the base. And we know that x here is the exponent. So any exponential expression has a base that's being raised to an exponent. That's essentially the idea. Now, I'm going to call, not that. I'm going to call, so that's the exponent, here's the base. And what I'm going to call y, I'm going to call that guy the result. The result. Yeah, we're going to use the word result, because it's the result of the base being raised to the exponent. Let me draw a little arrow there. Cool. So this is a general format of a exponential function. So what we notice, y'all, is that exponential expressions and functions have some base being raised to some power, and it's equal to some, the result. Now a logarithm instead does the following. Essentially, a log would be of this form. If I use the same variables, it would be log of base b. So any log has a base as well, and it functions the same, or it should be the same kind of base as the exponential. But instead, we would input the result. We would plug y in, and we should get out x, which is the exponent, the power, right? So essentially, guys, what a logarithm does is I say, okay, the log base b. So b tells me what base am I working with, right? Am I multiplying by 2s? Am I doing 2 times 2 times 2 times 2 dot dot dot? Or am I doing tens? 10 times 10 times 10 dot dot dot? So the b here is just the base. It tells us kind of where are we working. Am I working base 2? Am I working base 10, etc. What I do with a logarithm, though, is a logarithm is essentially telling us magnitude. Okay, a logarithm tells us magnitude. It tells us, okay, if I input this value y here into my log, the log is going to tell me what power, right? What power do I need to raise my base into? So I'm going to draw this with some blue arrows. So this logarithm is going to tell me, okay, it equals x because if I take b and I raise it to the power of x, then that will be equal to this result. Do you see that? B to the power of x equals y, so b to the x equals y. Oh, that looks familiar. You know why? Because it's the same as our exponential equation. All right. So the idea that I'm trying to get at, y'all, is that actually an exponential gives you the result of the products, right, of 2 times 2 times 2, whereas the log would take, 2 times 2 times 2 equals 8, right? The log would take that result and it would tell you what power you need. This log idea will end up being very useful in the case of equations such as, oh, what if I knew that 3 to the power of x was equal to 10? Well, there's no power of x which does that, but I can use a logarithm. And so I'm going to use my decoder ring to make the log. I would say a base of 3 with an input of 10 should equal this power, right? So log base 3, like I said, base 3, with 10 plugged into it, should equal my power, which is x. Now this log base 3 of 10, what's great is that we have calculators in our life which can evaluate that for us, all right? We'll talk more about how to actually evaluate these with a calculator in the future. So that's kind of what I wanted to get out of the way about slide 5. All right, so I'm going to go ahead and skip forward a little bit here. So yeah, you can read this on your own. If you just read it, it hopefully should make sense. Here it asks us to rewrite log base 4 of 28 equals x as an exponential. So I could actually do that using the decoder ring. If I have log base 4 of 28 equals x, I just got to use my decoder ring. 4 to the power of x equals 28. Right? 4 to the x equals 28. Y'all know how to write that. And then this is the practice. I'm going to leave that one up for you guys. I want y'all to do that yourself. And now we get to slide 9. This is where I kind of wanted to, this is the one I really wanted to talk about more. Now, I started talking about this at the end of class last time, but I felt like I could maybe do a better job of explaining it. So to start things off, I just want to remind y'all. So domain, if you guys remember, domain is the set of all x values which can plug into a function. Domain is a set of all x values which can plug into a function. Now, the range is the set of all y values which can be output by a function. All right, so that's kind of the general gist of these two things. So when we're looking at domain and range and we're asked to find the domain and range of these functions, what we're looking at, guys, is I wanted y'all to just kind of analyze the graph. Think about it, right? You see this graph here for the blue one. I said the blue graph, the blue function is f of x equals 10 to the power of x, all right? This blue line is 10 to the x. So what we can see here, y'all, domain, we're looking at, okay, what x values, right? That's the horizontal. What x values are allowed here for this function, the blue one? Well, if I look at it, it looks like it goes all the way to the left. So it seems like my domain should include negative infinity. All right. And what about how far to the right does it seem to be going? It looks like it's going to the right, and I know it's going up pretty vertical, but it looks like it's going to the right constantly. And if I look at the equation, guys, 10 to the x, I can plug anything into that, right? I'm allowed to plug anything into 10 to the x, right? I could plug in up to infinity, so I'm going to put in infinity here. Now, and then I'm going to close that off with another parenthesis. So that's my domain. Now, a better way to have typed this maybe to show you guys something, I'm going to use the function key. Remember, guys, this is how you type math. See, it even says type math. So I'm going to do a parenthesis minus, and then if I want to write infinity, you could pull it up with the keyboard here, right? You can see if I go to functions, oh, just kidding. Lol, I'm lying. All right, well, you can very easily type infinity in Desmos by just literally writing the word infinity, and it turns it into an infinity sign. There we go. That's the domain. What about the range, though? What about the range of this function? Range, we said, is the y values. Looking at it, it looks like it goes all the way up to infinity, right? So I know that I will have infinity, infinity as my upper bound. But what about my lower bound? How far down does this go? Looking at the line, y'all, it looks like it plateaus here going towards 0. Now, we're going to talk a little bit more in the next slide about why that is the case, but I just wanted y'all to observe that. So it looks like this thing is having a horizontal, right, left and right horizontal asymptote going towards y equals 0. So the range is going to be 0 to infinity. All right. What about log, though? Log is the red one. Log is the red one. So you can see it's kind of like a flipped version of it. In fact, it actually is a flipped version of it. If I took like this, if I cut out this square here and I folded it along a diagonal, the lines would perfectly line up with each other. I don't know if y'all remember from geometry, but that implies actually that these functions are inverses if you could fold them over each other across the diagonal line. That's a side note. So let's look at the domain. What x values are able to be plugged in? It looks like it goes all the way to the right. So I'm going to say domain is definitely going to have infinity on the upper bound, right? But what about the lower bound? What is the lower bound of this function? How far to the left does it go? It looks like it's actually going down, right? In a sort of a vertical asymptote, right? See how it's going up and down? So it actually, I don't think that this function is going to even reach 0, and that is actually the case. This function will not reach 0. That's why I have the parenthesis, by the way, y'all. Remember, if it actually could equal 0, I would have a bracket, right? I would have a bracket. But this function cannot equal 0, so therefore I use a parenthesis to imply that it is strictly greater than. In fact, guys, 0 to infinity with parentheses, this basically means just x is greater than 0. Strictly greater than, not without the greater than or equal to thing, right? Let's look at the range. What's the range of this guy? It looks like this guy is going all the way down to negative infinity. Cool. So negative infinity. And actually, if you look at it, yes, it's going slowly up, but it is going up, and it's actually going to go up forever. So it's going to go up to infinity as well. So actually, logs can have any output, yet you cannot plug in any numbers that are 0 or lower. Interesting thing about that. So we can actually observe, and this is for number 3, that the domain of the exponential is the same as the range, right? The outputs. So the inputs of the exponential are the same as the outputs, right? The range of the log. And the inputs of the log, the domain, is the same as the outputs, the range of the exponential. So they're kind of inversed, they're reversed versions of each other. Now that doesn't necessarily prove that they're inverses, right? But it does support the claim that they're inverses. Right? If they were truly inverses, then anything that gets plugged in to this function should be able to be outputted by the other one, and vice versa, right? This right down here is truly the definition of what inverses would be. If y equals f of x, right, then f negative 1, that means inverse function of y should equal x, right? Anything that I can output from one function should be able to be put into the other one and give you the original input. So that's kind of a little bit about slide 9. Moving forward to slide 10, we've got this thing here talking about the asymptotes. Now I referenced these in the previous one, but let's look a little bit at it. The function f of x equals 10 to the x has a horizontal asymptote at y equals 0, right? Here's y equals 0. It's the x-axis, right? Because that's where all of the values where we have a 0 for the y input, for the y value, are. So you can see that in the function, the blue one, for f of x equals 10 to the x, as x approaches negative infinity, this function will go towards 0, right? So hey, let me write that down here. So we said the limit as x goes to negative infinity. Remember, we talked about limits before. When I have 10 to the x, that will equal 0. And the reasoning is explained here, but basically, guys, if you think about it right, what is 10 to the negative infinity? Anytime you have a negative exponent, that will result in a reciprocal, so it's 1 over 10 to the infinity. 10 to the infinity, right, or just 10 to a big number, right, because infinity is not a real number. This is going to basically equal infinity, won't it? So I would end up with 1 divided by infinity. If I'm dividing an infinitely large number, then that will go towards 0, right? 1 divided by a huge number will become essentially 0. So that's kind of an explanation of why we have this horizontal asymptote here, all right? Now it asks us to use the concept of exponents in the decoder ring to explain why does log x have a vertical asymptote here? All right, so what we're going to do is we're going to go ahead and actually we're going to take this idea here, and we're going to use the decoder ring on it. Remember, the decoder ring says that if I have a base of 10, I could use it as my base of my log and put in this value, and that should equal the exponent. So I see that log base 10 of 0, or effectively 0, right? Because you can't actually plug 0 in. But we'll use 0 anyways as a placeholder for a very small number. That should equal the exponent, x. What was x? Oh, look, it was x was going towards negative infinity. So what I can claim then is that the essentially as I plug in small numbers, right, as I plug in essentially 0, my logarithm is going to go towards, oops, my bad, I accidentally lost my picture. X is going to go towards negative infinity. So how would I maybe explain that in words? I would say using the decoder ring, the limit of the log as its input goes toward 0 will go toward negative infinity. I feel like, to be honest though, the best way to see this is with the math. So what I've essentially proven here, guys, is that if I had like, log base 10, and I could just write that as log, right? Log base 10 of y, what happens as y goes towards 0? Well, as y goes towards 0, we saw up here that the log will go to negative infinity. So we're seeing that as my inputs, right, as my values that I'm plugging in, right, go towards 0, the function is going down to negative infinity. And that is simply because of this decoder ring. Now this next part asks, if the base of the log for g of x was a value different from 10, would there still be the vertical asymptote at x equals 0? We could very easily show this using the exact same process. So let's just, in fact, actually, you know what I'm going to do? I'm not even going to clear it all. I'm going to erase, and I'm going to show you that nothing changes. So what if I change 10 into, anything? Let's call it b. B as in base b. So the limit as x goes to negative infinity of b to the x will still equal 0, right? It doesn't matter. It doesn't matter what b is, right? Because b to the negative infinity will equal 1 over b to the infinity. And regardless of what b is, as long as b is some value that's like, positive, which actually in the definition of an exponential, it should be positive, then this is going to get bigger and bigger, and 1 over that big number will go to 0. All right. So we changed 10 to b, so let's change 10 to b here. So that means that if I do the decoder ring, I see that log base b of 0, right? Log base b of 0 is equal to x. What is x? Negative infinity. Therefore, no matter what your base is, it will always, every log, no matter the base, will have this vertical asymptote going towards x equals 0. And so that's actually a really important feature of logarithms. Essentially, guys, what this shows us is that a logarithm is only able to have inputs from 0 to infinity. It can only have positive numbers plugged into it. You are not able to take a logarithm of a negative number. So for example, like if I was told if I was asked to evaluate the log of negative 4, right? Let's say it's the log base 2 of negative 4. That will be undefined. Now, however, the log base 2 of positive 4 is 2, because 2 squared is 4. Hey, what do you guys know? Logarithms, guys, if you use the decoder ring, I swear, man, logarithms become a little bit easier to understand, I think. All right. Now, let's keep going. The rest of these slides, I'm going to go a little bit quicker through. Slides 9 and 10 were the ones that I thought were kind of a little bit hard to kind of get the understanding of, and so I was wanting to explain those a little bit more. So let's look at 11. 11, now slide 11 is just kind of talking, it's just really explaining an idea. All you need to really gain from this is that E is a number. E is a number, and it's kind of like pi. All right. It's just a significant number. It's very useful for us in modeling population growth, right? Like natural growth. So, for example, anytime that scientists are making models to predict the world population in 2025, they're using that base E. Um, I because of online learning, there's certain things that I kind of got to skip through, to be honest, because there's like I just have to focus on what's more important. So we're not going to really dive into why this exists, why E exists. I kind of need to ask you guys to just accept that E is some number. It's about 2.72. All right, it's about that. So the main purpose of this slide is just to show you what happens when I have a base E. We just write it as ln. That stands for natural logarithm. ln as in log natural. Okay. So then look at number 12. It says, what is a simpler way to write log base 10 of 15? Fun fact, guys, log base 10, that's called the common logarithm. And that's that idea where we can, instead of writing a base, we can literally just write log 15. What is a simpler way to write log base E of 6? As we saw in the last slide, anytime you have base E of your log, it is ln. So I would literally write ln of 6, and you can see right there, it actually gives me my answer. Moving forward, we have these tables here. I'm not going to fill out the whole table for you guys because I think y'all can do it. But essentially, I'm just asking you guys to use the decoder ring to identify what these what this log statement means as an exponential. So if I make x equal to 1, right? If I have log of 1, then I would get that 10 to the power of y equals 1, right? 10 to the power of y equals 1. That's using the decoder ring. Here, wait, let me visualize that for y'all on the whiteboard. So we said log of x equals y. This is base 10 technically because it's just the common logarithm. And using the decoder ring, I see that 10 to the y equals x. So if x is 1, right, then 10 to the y equals 1. And what power do I need to make it 1? Y should equal 0, actually. Okay, what about this one? What about x is 10? Then I would literally just write 10 to the power of y equals 10. What would y have to be then? 1. Who'd have thunk, right? 10 squared, so 10 to the power of y equals 10 squared. Yeah, this one's actually kind of easy. Look at that. What do you think y is? It's got to be 2, right? Because look, dude, they're the same setup. And so on, okay? Same thing here, except ln is base E. Y'all can do that. And here I've got base B. What do you think log base B of x equals y is going to make? Well, using the decoder ring, we will see that b to the power of y equals x, right? And you can keep going with that. Alrighty, y'all. Continuing on, here's just some practice. I will leave these for y'all to practice. If you have questions about these practice problems, by the way, or really anything, like let's say that you said, Mr. Hobart, I still don't get what you're trying to say in slide 9, right? Just go ahead and ask in the Discord. Okay, guys, message us in the math discussion. It could be so useful. Moving forward, talking about inverses. This one here, it says two functions f and g are considered inverses when essentially they cancel each other out, right? See how f of g of x makes x? So essentially f and g are just canceling each other out and just leaving us with x. So for example, if f of x equals ln of x and g of x equals e to the x, then f of g of x is ln of e to the x, right? To be honest, this whole slide here is a little bit extra. I'm gonna go ahead and say you guys don't really need to do this because we're gonna talk about this idea next time anyways. But I think it's a good exercise to try out. It's like show that these are inverses, right? Well, evaluate f of g of x. You guys have done this in algebra 2, right? So check it out, right? I can plug it in. Oh wait, oh dude, I left you guys a space to write it. So f of g of x would be f of g of x should equal, well, f of x is 1/2 plus ln of x. And what's plugging into f, right? G of x is. So actually g of x is going to be inside this ln. Do you see that? That's how we call these compound functions. This is how compound functions work. Essentially, what's the input of f? Oh, it's the whole thing g of x, right? It's the whole thing. Um, so what is g of x? G of x is e to the x minus 1/2. So let's write that down here. We have 1/2 plus ln of g of x. G of x is this. So e to the x minus 1/2. Interestingly, guys, remember logs and exponentials are inverses of each other. So what's going to happen is, I'm going to do it in red. These guys will actually cancel each other out. And what we would be left with is just the exponent. We'll be left with just the exponent. And so you'd be left with 1/2 from this guy plus, and then this exponent, x minus 1/2. And this whole thing will simplify because, right, the 1/2 and the minus 1/2 will cancel, and I'm left with just x. So they actually are inverses, these two functions. And then finally, guys, we got slide 16 here, where it is an exit check. I do want y'all to do this on your own because this is kind of one way for me to assess what y'all have learned. All right? That is kind of my little overview of these slides, some of the ideas. I hope that was useful. If it wasn't, feel free to yell at me in the Discord and be like, Mr. Hoba, your video sucked, and I'm upset, and then I'll try my best to make you less upset. All right, y'all. Have a good day, and I hope to see y'all on Friday.